Astronomers may have been reading the wrong spin on distant worlds because thick atmospheres whip around far faster than the planet beneath. This is Fascinating Frontiers, episode 163. Over the past week, the steady drumbeat of SpaceX launches kept setting new reuse benchmarks, while NASA and ESA moved forward on lunar payload contracts and exoplanet survey planning. At the same time, new telescope capabilities kept expanding the volume of data available for atmospheric studies and star formation mapping. Those threads set the stage for the stories ahead. A new study warns that cloud-level winds on Venus-like worlds can rotate up to 60 times faster than the solid planet itself, leading observers to mismeasure the underlying spin period. Multi-wavelength observations are proposed to separate the atmospheric signal from the surface rotation. The European Space Agency's Plato mission, launching in 2027, is expected to discover hundreds of such planets where this correction will be essential. The research highlights that reflected light from upper clouds dominates the photometric signal at certain wavelengths. Correcting for this effect requires simultaneous measurements across visible and infrared bands to isolate the slower surface contribution. On worlds like Venus, the upper clouds circle the planet roughly 60 times for every single rotation of the solid surface. Multi-wavelength data will be needed to disentangle the two components once Plato begins delivering hundreds of similar targets. The open question is whether any current or near-future instrument can reliably separate wind speed from true spin period across a statistically useful sample. Now, on a completely different note, on August 15, 1977, the Big Ear radio telescope recorded a strong narrowband signal lasting 72 seconds that appeared in only one of 50 channels and displayed the expected rise and fall pattern of a celestial source. No repeat has ever been confirmed despite repeated searches. The event remains the strongest unexplained candidate for an artificial extraterrestrial signal. The telescope's drift scan mode captured the signal as it crossed the beam, producing the characteristic intensity profile. Subsequent surveys at multiple frequencies have failed to recover a matching source. From that single unexplained radio blip, we shift to confirmed record of repeated, reliable launches that now define routine access to space. Two Falcon 9 rockets lifted off just 38 minutes apart on August 15th, one from Florida carrying 8 Globalstar satellites, and one from California for the U.S. Space Force. The Florida mission deployed its full payload into low Earth orbit to refresh the Globalstar constellation. The California launch supported U.S. Space Force objectives under mission designation USSF 366. Observers note that both vehicles returned to flight readiness on the same day, underscoring the fleet's current turnaround capability. The next step observers will watch is whether the same turnaround time can be sustained across multiple consecutive days. From rapid operational reuse on Earth, we turn to the long-term commercial shift in how NASA will explore the Moon. 3 additional lunar missions are scheduled for award this year under the Commercial Lunar Payload Services Initiative, one of which is an orbiter intended to succeed the aging Lunar Reconnaissance Orbiter. This continues the shift toward buying services rather than building spacecraft in-house. The orbiter would supply high-resolution mapping and communication support for future surface operations. Task orders will specify payload capacity and data return requirements for each selected provider. From commercial lunar services, we move to a fully autonomous mission concept that removes the need for constant Earth commands. NASA intends to send 3 small rovers to the lunar surface with only the instruction to divide the exploration tasks among themselves. Onboard decision-making will allow the vehicles to adapt routes and instrument use without waiting for Earth-based operators. Each rover carries sensors for hazard detection and resource mapping. The mission profile emphasizes cooperative behavior among the 3 units over a shared workspace. From robotic independence on the Moon, we turn to new evidence that one of Neptune's moons arrived violently from elsewhere. Spectroscopic data on Neptune's irregular satellites support the long-standing idea that Triton was captured from the Kuiper Belt, disrupting an earlier moon system. The tiny moon's compositions and orbits preserve evidence of that ancient collision and scattering event. The findings appear in Science Advances. Triton's retrograde path and dominant mass fraction indicate it arrived on a highly eccentric trajectory that scattered or destroyed prior satellites. The remaining small moons therefore represent fragments or survivors whose surface spectra match captured Kuiper belt material. Neptune's single large moon Triton outweighs every other satellite around the planet combined, yet it travels in a retrograde orbit that runs opposite to Neptune's spin. Imagine a city-sized body arriving from the distant Kuiper belt at roughly the speed of a commercial airliner and swinging once around the ice giant. Gravitational energy released during that encounter would have shattered or ejected any earlier moons that happened to be in its path. The surviving small moons we see today carry the chemical fingerprints of that ancient disruption, their surfaces and orbits recording the violence of Triton's capture. One surprising number stands out. Triton alone accounts for more than 99% of the mass in Neptune's entire satellite system. Spectroscopic measurements of the remaining irregular moons reveal compositions consistent with captured Kuiper belt objects, rather than material formed in place around Neptune. We can map the resulting debris distribution and even match it to spectroscopic measurements, yet nobody has a complete dynamical model that predicts exactly which original moons survived and which were lost. The lingering mystery is whether similar capture events occurred around other giant planets and simply left fewer traces behind. From ancient planetary violence, we turn to a quiet but persistent cosmic mystery that still resists explanation. Recent claims that dark energy might be weakening have been examined and found not to alter the overall picture of cosmic acceleration. The analysis reaffirms that the universe's expansion rate continues to increase, consistent with earlier supernova and baryon acoustic oscillation measurements. Follow-up papers are expected to refine the error bars on the dark energy equation of state parameter. The study compares multiple independent datasets to test whether any deviation from a cosmological constant appears at current precision levels. No such deviation reaches statistical significance in the combined results. From the largest scales of the universe, we turn to a simple yearly chart that helps observers know when the sky is most active. A new visualization plots the maximum meteors per hour visible on any night, incorporating both major showers and the sporadic background while accounting for moonlight. The graph indicates that mid-August and mid-December remain the strongest periods even after lunar interference is subtracted. Minor showers contribute little compared with simply observing on a clear, moonless night away from city lights. The chart corrects rates for observer latitude and includes separate curves for best case and average sky conditions. It demonstrates that background sporadic meteors provide a steady baseline throughout the year. From steady meteor watching, we turn to one of the most striking wide-field images released this week. The August 16th astronomy picture of the day shows the galactic plane rising above the geothermal landscape of Yellowstone National Park. The image combines foreground thermal features with the dense star fields of the summer Milky Way. The photograph records the contrast between steam plumes and the stellar backdrop without artificial light interference. Viewers can trace the galactic center region above the park's distinctive terrain. Fresh instruments in orbit are increasing the pace at which astronomers identify both stars and planets outside our solar system. The article highlights how improved sensitivity and wider fields of view allow detection of smaller worlds and fainter host stars than earlier missions achieved. Data from these telescopes feed directly into atmospheric studies that were previously limited to a handful of targets. Wider surveys now capture light curves and transit signals across thousands of stars simultaneously. The resulting catalogs supply candidates for follow-up spectroscopy that can reveal atmospheric composition. A 13-year-old observer in Northern California has been stacking lunar video frames with 7x50 binoculars and a phone adapter to improve surface detail. Nathan also processes radio data through Pictor and posts his results on Medium to draw peers toward telescopes instead of screens. His approach shows how modest equipment can still produce publishable quality lunar imagery when processing steps are applied carefully. Video stacking reduces noise and reveals crater rims and Maria textures that single frames obscure. Before we go, keep an eye on whether the next Falcon 9 turnaround cycle can match the same-day readiness achieved on August 15th. That covers today's space and science news. Share this with a fellow space enthusiast if you found it interesting. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nera Network. Links in the show notes. Quick tip from the network. Try the Do Positive Pod next. Good news in science and tech. plus one concrete action you can take. Every Nara Network show is free at naranetwork.com. And on the website, every episode's visuals live in our free image gallery at naranetwork.com/gallery. Royalty free under Creative Commons, download with attribution. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.